we used to make the error 0 in some selected points. So collocation means basically making close together. So here what we are doing, we are basically making our approximate solution and our actual solution very close. Okay, our approximate solution and our actual solution very close. So basically we are doing collocation. So how we are doing, we are basically making the error 0 in the selected point. Okay, so here what we use one weight function, that is our direct delta function, that basically value is equal to 1 at the selected point, and and at the rest of the point that value is 0. Okay, at the rest of the point value is 0. Okay, so basically what we are doing, we are basically using a weight function that value is 1. So whenever we'll try to find that residue W into R in the weighted residual method, we used to find that weight operating on the R that we are making is 0. Okay, in average sense over the entire domain. So here in the point collocation method, we are not doing the integrations. We are finding W into R is equal to 0 at the selected point of X, and here W is equal to 1. So basically we are making error is equal to 0 at some selected point. Okay, so here we'll take one example problem. We'll see how we can do that. So here we'll assume our trial function as a polynomial function. Okay, in the last video we have assumed our trial function as a trigonometric function, and we see how we can solve that problem. Okay, how you can use that collocation method to minimize the error in the selected point. Here what we do, we will basically assume trial function. Again, let me repeat it. Trial function also should satisfy the boundary conditions that our actual problem is satisfying. Okay, so here what we are doing, we are using one beam problem. Here we are using one beam problem. Okay, here we are using beam problem, and that beam is simply supported beam where our y displacement is 0 at x is equal to 0, and again y is equal to 0 at x is equal to L, and we have moment. So equation of the moment is ei dt by dx2 minus m is equal to 0. Okay, and we have our actual solution is this one. So we know. So we try to find our approximate solution, and we try to see what is the error is coming in the approximate solution using point collocation method, where we can use our trial function u as a plus bx plus cx square. Okay, in the last video you use this one, but now we'll use this trial function and try to solve our weighted residual method using point collocation approach. So here what we do, we have to put our boundary condition that u is equal to 0 at x is equal to 0. If we do, we will find a is equal to 0. Okay, we'll find a is equal to 0. Now again, second boundary condition, we have u is equal to 0 at x is equal to L. Okay, if we do that, we will find b in terms of c. Okay, we will find b in terms of c. So u is equal to 0. So here will be bl plus cl square. So we can write b is equal to minus cl. Okay, now if you put the value here, you will get our trial function u is equal to c into x in bracket x minus L. Now here again you can see initially we had three unknown. Initially we have three unknown, but we put our boundary conditions in the trial function. So trial function must satisfy the boundary condition which the actual solution is solving. Basically for our case, our physical problem, this is our one physical problem. So we have y is equal to 0. So also u should be 0 at x is equal to L, and y is equal to 0 at x is equal to L. Okay, so our u also should be 0 here. Okay, now if you put the boundary conditions, we can have our trial function or approximate function like this. Okay, and already we have obtained that our moment that is acting in the beam. So our beam is simply supported beam, and moment is acting there. The moment is m0. So our force equation, okay, or natural boundary condition is given here, that ei d2y dx2 minus m0 is equal to 0. Okay, now here why is it the actual solution? Okay, now what we did, we find the trial solution and we put the value of the trial solution in this equation, and obviously this value will not be 0. If you put u instead of y, this value will not be 0. This will be called error or residue. And what we do, once we find the residue, what we will do, we will try to basically make the residue 0 by multiplying some weight function that is equal to 0. Since we are discussing point of collocation method, in that point of collocation method, we are not doing the integration, we are making the error 0 in the selected point. Okay, and here the w is our direct delta function. The value of w is equal to 1 at that selected point. Okay, and in rest of point it is 0. So w is equal to 1. And here you just see we are choosing one point x is equal to L by 2. Now at which point we should choose, that depend on the number of unknown variable we have in that trial solution. Okay, if we have more number of unknown variable in the trial solution, then we have to choose more number of the same number of collocation point, and we have to make the error 0 in that selected point, and we will have that number of equation and we can solve that. Okay, so here we are choosing only one point, that x is equal to L by 2, and if you put the value, we'll find that C, value of unknown, that is equal to m0 by 2 ei. Okay, now what is our approximate solution? Our approximate solution will be like this. So if you put the value, we'll get our approximate solution as u is equal to minus m0 by 2 ei x into L minus x. Okay, and also we know that our actual solution look like this. So here you can see our approximate solution and actual solution is the same. So if you plot it, you will get graph like this. This is our approximate solution that also will overlap with our original solution. Okay, so this is the way we can find our approximate solution using point collocation method. I hope you got some idea. Thank you.